Again, good morning and good afternoon, everybody, and welcome to those who may be watching this recorded. My name is Stephanie Lewis. I will be your moderator today. I welcome you to another National Institute for Congestion Reduction webcast. Um, my name. It is my pleasure to welcome you to Using Traffic Signals to Decongest Cities. It may be simpler than we thought. Our presenter today will be Michael Cassidy. Let me tell you a little bit more about him before I hand the presentation over. Michael Cassidy is the Robert Horan Jeff Professor and Chancellor's Professor of Civil and Environmental Engineering at the University of California, Berkeley. He received a doctorate in civil engineering from Berkeley, served for nearly 4 years as an assistant professor in the School of Civil Engineering at Purdue University in West Lafayette, uh, Indiana, and joined the Berkeley faculty in 1994. He is currently an associate editor of the journal Transportation Research Part B. He is a member of the International Advisory Committee for the International Symposium on Traffic, uh, Transportation and Traffic Theory, uh, and a former director of the University Transportation Center for Federal Region 9, and a vice chair in Berkeley Civil and Environmental Engineering Department. His research interests focus on transportation planning management, particularly in the areas of highway traffic, public mass transit, and multimodal systems. With that, I'm going to hand the presentation over to Dr. Cassidy. Mike, take it away.
Thank you very much, Stephanie. How do I sound? Can everyone hear me?
I can hear you perfect.
Okay, wonderfully. In that case, I'll say thank you, Stephanie, for that lovely introduction. And thank you for this opportunity to speak on one of the NICR sponsored research efforts that I've been involved in with the colleagues you see here. Now, the topic for today pertains to the use of traffic signals to decongest cities. Okay, I'm going to present today some new strategies for coordinating traffic signals on all-way, or we might say four-directional street grids. Now, the strategies that I'm going to present have surprisingly little in common with the many strategies that presently exist for coordinating network traffic signals. And I say this because the existing strategies tend to be quite complex, but the strategies that I'll present are very simple. They are simple for me to explain. I think they are simple to understand, and they would be simple to implement in real settings. And yet, I'm going to demonstrate that these simple strategies can dramatically outperform the existing complex ones, and that can be based on whatever metrics one might be interested in using. So we only need a minute or two of background, and I want to assure you that when distilled to their essence, the ideas at play here are really quite simple. This is because the game is to synchronize offsets. And offsets are the elapsed times between the initiations of directional green indications across neighboring traffic signals. So one synchronizes offsets to enable as many vehicles as possible to pass through as many intersections as possible without seeing a red phase. Now, this, of course, would increase the rates the trips are completed on the network, which in turn reduces congestion and delays. And I'll mention as the aside that one typically uses a signal cycle length that is common to all signals on the network, so that the offsets, once they are established, can be maintained cycle after cycle. Now, synchronizing offsets is regarded as a difficult challenge on four-way street networks. And to see why, let's look at this rectangular street grid. You notice we have unequal block lengths, which is common in cities. Well, suppose we consider first the horizontal streets that serve traffic in the east-west travel directions. In undersaturated traffic, meaning where we do not have residual queues, it's generally quite easy to perfectly synchronize offsets for one direction of travel. Let's say we decide to do that for the westbound travel direction. That's fine, but having done this, the offsets for the signals are now cast in stone, and we should not expect that these offsets that work well for westbound travel are also going to work well for eastbound travel. In fact, the eastbound direction now is likely to see a lot of red phases during its trips, especially since we have unequal block lengths. And what about the orthogonal northbound travel directions? Well, here again, we should not expect that the offsets that we've chosen to benefit westbound travel are going to work well for the northbound and southbound directions too. So herein lies the rub. Once we establish offsets that work well for one travel direction, like the westbound direction, how then do we get good synchronization for the other three travel directions? That is really the challenge. And the traffic science community has responded to this challenge by proposing numerous complex solutions. Basically, I would say these try to jiggle or balance offsets in some ways so that all travel directions enjoy good signal progression. But successes, to me, seem rather meager, at least to date, and the proposed solutions seem to grow in complexity over time. And speaking personally, I am not convinced that we're going to get anywhere by adding one or two more complex elements to already complex methods for coordinating network signals. So suffice to say, when my colleagues and I decided to try our hand at coordinating network signals, we were not going to build upon somebody else's already complex ideas. Instead, we decided we'd start over. We sort of wipe the slate clean and start from square one. And in doing this, one of the first things we did was look at one-dimensional networks, meaning we looked at signalized arterials where we are concerned with synchronizing signals only for traffic traveling in two opposing directions. Again, you'll notice we have unequal block lengths. So again, when we establish offsets for, say, the westbound travel direction, those offsets probably won't work well for the eastbound direction. It's kind of a funny thing because when traffic engineers were confronted with this simpler two-way system, they saw a logical path forward. They made a concession, really. See, traffic engineers have long ago decided that if one cannot get good signal progression for both travel directions on a two-way arterial, then one might synchronize the offsets for the heavier flow direction and not worry about the opposing lower flow direction. Now, this concession is logical because prioritizing the heavy flow direction can result in higher trip completion rates, meaning lower congestion and delays, as opposed to, say, an ill-fated effort at some compromise to treat both travel directions equally. And by the way, we know that cities, even sprawling cities like Los Angeles and Atlanta, have neighborhoods that are rich in workplace destinations. So our logical concession, seem to be a little slow here. So our logical concession for four-way signalized networks was to synchronize offsets to favor vehicles that are heading inbound toward any neighborhood that's rich in destinations during the morning rush, because this is typically where typically the heavier flow direction on any street link in the network. We're not going to worry about the opposing travel direction on each link. And then we'll reverse things for the evening rush. We'll synchronize offsets to favor outbound traffic heading away from workplace destinations. Now, this turns out to be a good start, but it's not going to get us out of the woods quite yet. This is because for inbound traffic in the morning, for example, that traffic may come from all four travel directions, the north, the south, the east, and the west. And inbound trips often need to change direction. They may start out northbound and change direction, for example, or we might see the mirror image. And what about cities with multiple workplace-rich neighborhoods? What should we do about these complications? Well, we're going to make another concession, and this one is based on network science. Some years ago, a scholar named Michael Smith demonstrated that when controlling traffic on a network with route choice, it can be counterproductive to optimize each network node. That means to optimize with signal timing at each signalized intersection in this context, based on local traffic conditions at these individual nodes. One should instead, according to Smith, develop control strategies that focus on the network in its entirety. And yet, none of the existing complex strategies for coordinating network traffic signals have taken Smith's admonition to heart. Instead, every strategy determines and allocates green times needed individually at each signalized intersection. So some intersections might need and receive more green times on their north-south streets, while others on their east-west streets. And what we end up with is a network where each intersection's traffic signal has its own signal timing plan based on local needs. I want to emphasize that this is customary practice. It seems to be invariant across all coordination methods that currently exist. But our strategies instead do what Smith admonishes. They use the same signal timing plan, meaning the same green times, for all signals on the network. Now, there are various ways of determining what that common green plan ought to be. We might, for example, average the number of lanes across all streets in the network. But you see, by deciding to synchronize offsets, why do we do this? Why do we do this? Well, because by deciding to synchronize offsets only for the orthogonal inbound directions in the morning and only for the outbound directions in the evening, and by using a common signal timing plan, and finally, if we assume for now that the network forms a perfect rectangular grid, then that opens the door to signal coordination plans that are extremely effective, meaning they can outperform any plan developed by existing methods. Because, largely, we can focus on the network in its entirety. And these strategies turn out to be simple. To illustrate, I seem to have a, okay, there it goes. To illustrate what's possible, okay. Seem to be, Stephanie, my slides aren't quite, there it is.
It seems like there's just a little bit of a delay.
Yeah, and my slides are renumbered too. Okay. All right, to illustrate what's now possible, well, let's suppose, again, just for now, that our network is a perfectly orthogonal or rectangular grid with two parallel streets running north, south, and east, west. Now, we can have unequal block lanes like you see here, and we'll suppose that every intersection is signalized. We'll assume that the network has one or more neighborhoods that are rich in workplace destinations during the morning rush, like this downtown area you see here. It now turns out to be simple to provide excellent signal progression for all traffic headed inbound toward the work areas in the mornings and for all outbound traffic in the evenings. So what we can provide is exceptionally good progression over the entire street grid, no matter how large that grid might be, so that the bulk of commuters enjoy good progression over the full length of their trips, even though their trip paths likely entail two directions of travel. So suppose for starters that the grid is undersaturated, meaning that it is not plagued by residual queues. Imagine a morning commuter headed for this downtown. Perhaps she first travels northbound, maybe through many intersections, and she never sees a red phase. Then she turns westbound, where she will see a red phase at the very next intersection, but thereafter she might travel all the way to work without seeing another red. And the same could be true for any other inbound commuter in the morning, like this one. Now, when the intersections on the grid become oversaturated and exhibit residual queues, well, then we propose switching to a synchronization mode that does cause drivers to see red signals at some intersections. But this strategy that I'm going to talk about reduces congestion and delay on oversaturated grids far better than anything we've seen in the literature, and the strategy remains a simple one. And keep in mind, as I've said before, we can reverse things in the evenings to get this same quality signal progression when commuters leave work and head home. And we can do this with multiple downtowns, when the city has multiple downtowns. And very importantly, we can do it for more realistic networks that are not laid out as perfect orthogonal grids. Now, how do we do this? Well, once again, offsets, meaning the elapsed times between green initiations at neighboring signals, are going to be key here. And in this work, we're going to measure offsets at an intersection J, like you see in the slide, relative to a reference intersection located somewhere else on the network. So first, let's demonstrate how we might choose these offsets using this small grid But keep in mind that the idea works the same for very large grids as well. Now let's suppose that we have a single downtown area. In this example, we'll say it's on the lower left side. And we're going to say that workplaces where commuters are destined in the morning are clustered throughout this downtown area. Workplaces with many and few employees are represented here by large and small blue circles. And all these workplaces, all these locations where people work have a center of gravity. So let's suppose the center of gravity is right here in this case. Now recall that we'll measure offsets relative to a reference intersection, and we will take that reference intersection to be the one closest to the center of gravity of the clustered workplace destinations, meaning in this example, the reference intersection is the one shown with the red circle. Now here's the thing. Every link on the grid will be synchronized in the travel direction that is likely to carry most traffic inbound in the mornings, meaning we'll do it for the links, we'll synchronize for the links pointing toward the reference intersection near where workplaces reside. Note the examples of the inward pointing links that I've shown here. Notice that they consist of both horizontal and vertical links. Now I want to explain how to obtain synchronization in two orthogonal, or for example, two inward pointing directions. To keep the discussion simple, let's assume that all street links are homogeneous, meaning they all have the same fundamental diagram. So then we're going to have equal green splits at all intersections in this simple example. Now for a morning rush in undersaturated conditions, recall that the objective is to achieve forward progression that's focused toward the reference intersection. We're going to call this focused forward progression, or FFP. Thus, let's see here, thus the offset for an intersection J is simply the free flow vehicle travel time on the shortest path between intersection J and the reference intersection. That is the simple formula shown in the first parentheses with modulo cycle length. So in other words, suppose that the travel time between this intersection J you see and the reference intersection is 100 seconds. And further suppose that the common cycle length on the network is 90 seconds. Well, that just means that for a given inbound direction, signal J will turn green 10 seconds before it turns green at the reference intersection. It's that simple. And as a result, every link pointing to the reference intersection will enjoy focused forward progression. In other words, in the morning, we'll have focused forward progression on every street block in the inbound directions, such that all inbound vehicles, once they get started, and as long as they keep moving closer to the reference intersection, will have to stop at no more than one intersection due to a red phase. Now, this is possible in part because in a single given travel direction, all signals have the same green time. So an inbound vehicle that travels straight through an intersection without turning, say at the start of a green, reaches the next downstream intersection at the start of its green, and so on down the line. And for that matter, an inbound vehicle that travels straight through the intersection near the end of its green reaches the next downstream intersection near the end of that green, and so on. We get perfect progression except when you turn. Then the driver will encounter one red over the trip. This will work no matter how long the trip might be. And the reason all this is true is because on a grid, every inbound pointing link lies along a shortest path to the reference intersection. That's the genius here. And we can synchronize all intersections in this fashion, say over an entire citywide grid, or we can restrict synchronization to select zones within the grid. Now, all this we've been talking about are for undersaturated traffic conditions. But as the morning rush wears on, residual queues may form and grow, such that operations become oversaturated. Now, we know that once street links have persistent queues, then forward signal progression is not going to work very well because forward moving platoons are going to be impeded by those queues. But you see, even with these spillover queues, Morning commuters should still predominantly use links that point toward the reference intersection. So we can continue to focus on these inbound links. But we no longer seek a focused forward progression. Now, instead, what we do is we synchronize offsets to the backward waves that propagate through cues, as per something called kinematic wave theory. So you see, in the oversaturated case, offsets are once again synchronized for the shortest paths that point to, or we can say that are focused toward, the reference intersection. The only difference is that before, when we had undersaturated conditions, we might think of an observer who sees green phases by moving forward in a free flow vehicle. But now, in oversaturated conditions, we might imagine an observer who sees green phases by traveling backward along waves that travel at the wave speed w. So you see the offsets are established, as you see here, much like before, but now we're going to call this focused backward progression, or FBP. So let me explain really what happens here with this focused backward progression. The idea is that the green phase at an intersection J is going to be initiated only when the tail of the cue downstream starts to move forward. As I'm going to show you with this animation, I want you to note how the green signal appears at upstream intersection J only when the tail of that downstream cue starts moving forward. So here we've got a green at the downstream intersection. Now the cue is moving forward, so we get a green at intersection J. So traffic discharges through the green at intersection J without being blocked by the downstream cue. And just like before, we can apply this focused backward progression over an entire citywide grid, if that's what we want, or we can apply it to just any zone within the grid, say if only a particular zone becomes oversaturated during the rush. So then, what we're ultimately proposing here is an adaptive strategy, but it's not adaptive in the customary sense where signal timings might change at each intersection on a network based on local measurements. No. What we propose is not a local-based or an intersection-based adaptive strategy, but rather a zone-based strategy. So imagine at the start of a morning rush, all intersections on the grid might be undersaturated and therefore synchronized for focused forward progression. Then, as some zones become oversaturated as the rush wears on, the synchronization in those oversaturated zones is made adaptive by toggling between focused forward and focused backward progression. Now there's a small detail here. As offsets change, that is, as we toggle between forward and backward progression, the transition needs to be smooth and safe, but we've offered various simple algorithms to ensure that. More interestingly, in the evening rush, the directed vehicle paths now fan away from the reference intersection as commuters leave work and head for home. So in this afternoon case, we set the offsets using the same equations as before, okay, except that the signs now change for the speeds of the moving observers. And what we get here is something we'll call dispersing forward progression for undersaturated conditions and dispersing backward progression for oversaturated conditions. And recall that we can apply these ideas when we have widely separated workplace clusters, as well as spatially dispersed workplaces. And very importantly, we can adapt these ideas in simple ways to apply them when our real-world street grids are geometrically irregular. So why don't we see then how these ideas hold up under various scenarios? I want to test these ideas now using simulation. And we used what's called the AIMSUN microscopic traffic platform for our work. Let's take a quick look at a simple case. What we have here is a grid formed by two perpendicular sets of 20 parallel but unevenly spaced streets, like you see here. The separations between the streets range from 150 meters to 250 meters, like what we might see in many cities. And the streets have two lanes to serve each direction of traffic. For simplicity, we'll just say that the streets are homogeneous, meaning that they all have the same fundamental diagram. Now, we're going to take this shaded centered zone of 6 by 6 streets, if you see there in the picture, That's going to be where we activate adaptive control and toggle between forward and backward progression as needed. Now, each intersection's traffic signal will have a 90-second cycle, and they'll have two phases in each intersection with equal green splits because the street links in this example have the same number of lanes. Now, as far as demand goes, we're going to say the trips are generated at the rates shown by this cumulative count curve. And we'll say that in our basic scenario, well, we have a morning commute where workplaces are distributed over space as per what's called a Gaussian or a normal distribution. And that distribution of workplaces is going to be centered in the middle of our network in such a way that 40% of the workplaces lie within the 6x6 central zone. And we'll use a critical density in that zone to toggle between forward and backward progression as needed for that zone. Okay. Now I should say that with these inputs, our 20x20 street grid becomes congested no matter how we coordinate the signals. But the severity of the congestion will depend on what we do. So let's start by looking at that congestion. Let me explain what I'm showing to you here. This is something called a sample path of vehicle accumulation on the x-axis. In other words, the number of cars on the grid on the x-axis. And on the y-axis, we have the trip completion rate. And all this is for a single 3-hour simulation when we coordinated all the signals on the grid with zero offsets, meaning when green times, say for the east-west streets, are all initiated at once across the entire grid. This, by the way, and many of you know, is a very common strategy used when a network is congested. Now, let me explain the numeric labels you see here on this path. These are time steps. They are the elapsed minutes of simulation. You'll see how conditions devolve. This is what I want you to notice. Conditions devolve to their worst from minute 60 to minute 120. Because there I want you to note on the right-hand side of the picture, the high accumulations, that is the high congestion, and the low trip completion rates. You might also notice that after minute 120, the network gradually decongests because demand dies. But I want you to keep in mind that congestion reaches its peak on the grid at minute 120. So now it's reasonable to ask, can we do better at lessening this peak congestion than what is achieved by using zero offsets? Can we use another strategy for timing the signal? And yeah, we can. But what other strategies might we test here? Because there are lots of strategies out there in the literature, and they all claim to be effective, yet we can't test all of them. But one thing we noticed is in the literature is that whenever somebody develops a new strategy for coordinating network signals, the authors often compare their strategy against a computer program called Synchro. Synchro is something that adjusts coordination schemes iteratively until reaching a best performance. Now, invariably, we find in the literature that the new proposed coordination plan that's always tested against Synchro always ends up outperforming Synchro, but only marginally. Authors report improvements of just 1 to 5%, depending on the metrics they use over Synchro. So since Synchro seems to be a gold standard, we wondered how our strategy would compare against it. Could our strategy outperform Synchro by more than just 5%, say? And would that be true for any metric we might think is useful? So we pursued this question, and suffice to say, we set up the test to be as fair to Synchro as we could. Again, I just want to call your attention to this darkened data point. It marks the state of network traffic at peak congestion at minute 120. And again, this is when we used zero offsets. Now, this triangular data point is the state of network traffic at the height of congestion, meaning at minute 120, when Synchro was used to coordinate all signals on the grid. Synchro, by the way, changed our green times and cycle lengths and so forth, because that's what Synchro does. Well, you notice that Synchro lessened peak congestion. You see there's less accumulation there. In fact, it's reduced by about 15%, which is great. But here's what happened at t equals 120, meaning at the peak of congestion, when we deployed our adaptive strategy. You see the red circle there? Our method reduced peak congestion by more than 40% relative to zero offsets, and by 33% relative to synchro. And just keep in mind that 33% is a lot more than 5%, which is the best that other coordination schemes do against synchro. Now, I'll just throw in here, a staunch defender of synchro might complain because our adaptive strategy toggles between backward and forward congestion backward and forward progression to battle congestion in that center 6x6 zone, while synchro, on the other hand, always looks for forward progression only. This is really a problem with synchro, and it's a problem with just about all the other methods as well. But you see, when we deactivated our adaptive strategy and we used only focused forward progression over the entire rush, we still outperformed synchro by a wide margin, as you see here by the green squares. Okay, let's look at another metric here. Let's look at maximum congested footprints on the grid at minute 120, which was the peak of congestion. In the upper left, you see the footprint of maximum congestion under zero offsets. Next to it on the top, you see what happened under synchro. And on the bottom row, you see the peak congested footprints when we used our focused forward progression alone. And then finally, in the lower right corner, you see what happened when we used our adaptive strategy. The footprint is smaller on the bottom row. And the important thing here is that these smaller footprints mean that our strategies put an end to congestion earlier in the rush. That is to say, congestion would persist for shorter durations. To see this, look at these congested footprints later in time at minute 150 when the grid was decongesting. Now, with zero offsets, we still have a good deal of congestion at minute 150, and the same is true with synchro. But with our focused forward progression, there's only a little congestion that remains at time 150. And with our adaptive strategy, congestion disappeared entirely from the network by that time. So it seems that our method does a pretty good job at decongesting grids. But let's look at one final metric. What we have here is a time series of the grid's simulated vehicle accumulations, meaning the number of cars on the grid. And this is what occurred under zero offsets. Now recall that the area under this curve is the total vehicle hours traveled, or the VHT. So that's the total VHT on the grid. So what we want are smaller curves with less area underneath. Okay. Now with zero offsets, the curve you're looking at here, the grid exhibited nearly 22,000 vehicle hours of delay, which works out to about 13 minutes of delay per trip on average, which is typical of congested cities. Now, it turns out that synchro does a bit better. It reduces delay by 7%. But now look how much better our adaptive strategy does. It reduced delay relative to zero offsets by more than 30%. It erased about 4 minutes of delay from the average trip, and that is about 5 times better than synchro did. So our method just doesn't outperform synchro by 1 to 5%. In fact, we think our method did so much better than synchro because synchro optimizes green splits at each intersection based on local traffic conditions. In fact, all the methods do this. But you see, this makes it just about impossible to synchronize offsets network-wide. So at this point, we decided to disqualify local-based approaches to optimization, like synchro, and we said we're just going to look at a variety of scenarios where we compared our methods against zero offsets. And just to very quickly run through this, our method was very superior in the evening rush when traffic was mostly headed outbound. And our method was mostly superior when the workplaces were spatially dispersed, like they might be in a city like Los Angeles. And our method was superior when we had multicentric cities with multiple neighborhoods that were rich in workplaces. But maybe the biggest question is, hitting the wrong button here. Maybe the biggest question is, what happens if a network is irregular? What if it's not a perfect rectangular grid? So in this example, we took our original 20 by 20 rectangular grid, but to each link we added a zero mean random link length. The standard deviation for this added length was commensurate with what we saw in downtown Los Angeles, which is about 20 meters. So we get this irregular grid you see here. What we do is we use an auxiliary rectangular grid. That is, we take a kind of an average of this grid. It's a grid that is topologically equivalent to the irregular grid you see here. And what we do is we use the simple formulas that I showed you earlier to get offsets for our auxiliary rectangular grid. And then we use those same offsets on the real irregular grid. And when we did this, we saw that our method reduced delay on the irregular grid by 22% relative to zero offsets, which suggests that our approach can work pretty well in real settings. Of course, all these findings are from simulations, so the realism of the outcomes is always going to be an open question, especially when it comes to driver navigation. I mean, how do drivers navigate around queued traffic? Maybe the bigger question is, how well is our strategy going to perform when real-world conditions get further and further from our assumed conditions? Most notably, for example, what if the network is not laid out as a grid with four-legged intersections? What if the network consists of many five or six-legged intersections, say because there's a lot of diagonal streets? Well, even here, even for complex conditions like this, there may be ways to make our simple strategy work very well. In perhaps many cases, like Midtown Manhattan, one might be able to identify an underlying grid on the real-world, more complicated network by ignoring a few streets and intersections on that real network at first, and then coming up with the ideal strategy, signal timing plan for the underlying network, and then test and see how it works on the real, more complicated network. We think these ideas would be worth field testing because we think even for the most complicated networks that one could imagine, these simple ideas might be a good starting point for determining how to coordinate the signals. Anyway, this concludes what I wanted to say. I'm most grateful for your attention. If there are any questions, I'd be happy to try to entertain those. Stephanie, I guess I'll let you take it from here.
Thank you so much, Mike. Does look like we have a couple questions already in the queue.
Okay.
Just a really quick reminder before we ask you, Mike, all the hard-hitting questions. I just wanted to remind everybody that you do have access to that Q&A box in the lower right-hand corner of your screen. Just simply type in any questions and or comments you have. You do have access to all of the links above and a copy of today's presentation. So let's start with the first question. It says, how does this work when you overlay diagonal arterials on a grid network, such as in Washington, D.C.?
Yes, Mr. Smith, you maybe noticed I anticipated your question in my final comments. I do think that this method could still work as a good starting point for the kind of example you cite here. In fact, Washington, D.C., of course, was exactly the same city I had in mind when I was talking a few minutes ago. I think you would try to find the underlying network and coordinate the signals for that idealized underlying network, and then lay in the real network, do some simulations and see how well things perform. You may have to do some tweaks. You may have to do some adjustments for those extra legs, for example. But I still think that the simple ideas I tried to convey this morning or this afternoon for you, maybe, is really a good place to start rather than going with some computer science approach or technology heavy approach. I think start looking at these things as simply as possible, come up with a good strategy for idealized conditions and adjust them from there to accommodate your more complex real world conditions like diagonal streets or like very short streets or whatever you might conceive of. Does that answer the question? I don't know if there's any way you can affirm that this answers the question or not. Maybe what I should do, Stephanie, is go on to the second question.
Sure. And then if it doesn't answer the question, the best way to do it would be just to kind of type in a follow-up question in that Q&A box, and I'll read that out loud.
Okay. So I really appreciate the second question. Have we tested the strategy on a grid where the blocks links are very uneven, short and long? So, yeah, well, that's what we tried to do in the last test. We did. All the links were randomly changed in length, and what we did is then we kind of took an average auxiliary network based on that irregular grid, and we came up with signal timing plans for the perfectly rectangular auxiliary grid, and then we put them on the noisy real world grid, and things worked pretty well. Now, the other thing is, and not in a CBD. Here's the thing. I didn't I spoke longer than I really wanted to as it was, but in our paper and in our experiments, we looked at all sorts of spatial distributions of workplaces, including cases where there really was no downtown, but in fact workplaces were completely uniformly distributed over space. Now, in that highly unrealistic case, most even cities like Atlanta and Los Angeles tend to have certain downtown areas. But if a city didn't, if a city really had spatially uniform workplaces, then our method doesn't work quite as well as zero offsets, and it probably doesn't work as well as some of these other methods like synchro. But as long as you have some degree of clustering, not necessarily a heavy degree, but some degree of clustering such that you get inbound traffic in the morning and pronounced outbound traffic in the evening, that is to say, you've got directional differences during a peak, then this is a nice method to go with, I think. I hope that answers the question. But again, if it's an idealized case where there's absolutely no clustering of workplaces are uniformly distributed in space, no, this method isn't the best. It won't be. It's kind of unrealistic case. Okay, Mr. Smith, how to deal with bus rapid transit signal prioritization schemes? Yeah, what we were looking at, I'm not going to answer your question very well, I think, but we were looking at very congested cases in all our simulations. And the problem sometimes with signal priorities is if you make things worse for the car traffic, you have to, I guess what I'm saying is you need a prioritization scheme that won't mess up car traffic too much, because if you mess up car traffic a lot, that might come back and bite you by damaging the buses. I mean, you might have exclusive bus lanes, but even those exclusive bus lanes are not necessarily immune from extra congestion from cars. Sometimes extra congestion from cars will slow down the buses and undermine your efforts to improve bus travel. That's sort of some experiments we've been doing lately. I don't know if that makes sense, but maybe that's something we can talk about more. It's a kind of a topic that's of interest to me. But you really have to be careful with when you have a lot of car congestion. You don't want to do anything that's going to damage that congestion more, because it could come back and make things worse for the bus as well as for the cars.
Okay. Mike, what's the next step with this research? Is there a part 2? Can you talk a little bit about that?
I'd like people to learn about it. Maybe some people, I think I'm going to have colleagues. Well, I know I have colleagues who are going to kind of reject this work because they've been involved for many years on coming up with sort of complex solutions that involve black boxes like artificial intelligence or machine learning, reinforcement learning, and so forth. But you use those strategies when you've decided you have such a complex problem. You're not going to be able to simplify it and work things out for yourself. You need the computer science to do it for you. I don't think this is the case with network coordination. So I'd like people who believe that this might be the case to sort of try it in their jurisdictions, in their cities, for example. I think the first step might be, not to take idealized cities like we've simulated, but do a simulation of their actual city with all its myriad details and see how well this simple strategy works in simulation. And if it works well, then maybe try it in a field test or a demonstration project. I think the tricky thing about these field tests and the demonstration projects are getting really good measurements before and after to make sure the impacts that the strategy is having are those that you really want. I think that's what would be difficult, but I hope it might happen. I see another question. Recently, there is some talk about using the opposite of synchronization to lower speeds in favor of safety. Yeah, okay. There's always a trade-off between capacity and safety. I wish I could say I'm the paradigm of knowing where the line is, where the line is between those two opposing forces. I'm not. There's an awful cost. There's a terrible cost to making traffic worse, even if you can make it safer, which is a good thing. A lot of externalities associated with car congestion, environmental, of course, economically, quality of life, and so forth. So my interest lies in figuring out how to make those externalities minimal, how to make congestion less. I would say that there's nothing unsafe about what I've proposed today, But if someone thought it would be safer to coordinate signals really poorly, and someone made the decision that that's really the most important thing, then, well, go ahead. But now there's downsides to that. Thanks for that question.
Okay. So the next kind of, this sort of addresses this question sort of addresses something that you already mentioned, but I'll read it anyway. It says, what might be the first step in implementing these ideas in a real city, say as a field test or
Yeah.
demonstration project? And what might be the greatest challenge in evaluating the success and failure of the test?
Right, right. I tried to answer that question anticipating or having seen it. Yeah, I think the first step, if you believe that the simple approach might be the way to go rather than a computer science-based approach, you really need to simulate it in your own city with all the peculiar details of that city, all the short links, all the irregularities, all the heavy pedestrian traffic, and so forth. See how it works. If you can get it to work well in simulation, then try it in a test bed, try it in a demonstration project, and just kind of make sure you measure things carefully to see what the actual impacts are. Those are the barriers. Those are the barriers. All I can do as a researcher is say, look, this idea holds promise. I can't say that it's going to work great in Lubbock, Texas, or Chicago, Illinois, or anything like that. I haven't really tried it there, but I think even in the most complicated networks, this way of thinking about the problem might be the best first step. And see if something can be adapted from there.
All right. Well, it doesn't look like we have any more questions or comments. So what I'm going to do is I'm going to open up the evaluation for each of you on your end of the screen. If you could take a few moments to complete the evaluation, as the feedback provided is not only important to our presenter, but also the entire NICR webcast series. If you have a topic that you would like to hear a little bit more about, uh, please also make sure that you include that in the survey. So, on behalf of the staff at the National Institute for Congestion Reduction, thank you so much for joining us today, and we'll see you all real soon. Bye, everybody.